Experimental chemistry. Pure substances are defined as substances that are made of only one type of atom or only one type of molecule, that is a group of atoms bonded together. For example, diamond. Mixtures. A substance made by mixing other substances together, or a combination of different things in which the component elements are individually distinct. For example, sand. How can we recognize a pure substance? Pure substances have distinct fixed boiling and melting points. Chromatography is also used to determine the purity of a substance. Presence of impurities. Impurities lower the melting point of pure substances. Impurities raise the boiling point of substances.
Hello everyone, and welcome to another Simple Science video. And in this video in our IGCSE Chemistry Revision series, we will be looking at pure and impure substances. So in our daily lives, we encounter substances that are not always pure. Alright? And I can confidently say that most substances that we encounter are in fact impure. Alright, so most substances are being adulterated, but for good reason, or they're in nature, they're there for a good reason. Alright, so we're looking at substances like salt water, where it's a mixture of salt and water; steel, where it's a mixture of carbon or any other elements inside our iron structure; and air, it's a mixture of gases. Alright, so a pure substance would be a substance that has nothing else apart from the primary substance mixed in it. So in our control volume, we can see there's only homogeneous type of substance in it. So we're looking at distilled water, where there's only H2O molecules, and chlorine gas, where there's only chlorine molecules, and gold. And notice that I'm saying that there's a homogeneous spread of the homogeneous type of elements and compounds. All right, so it's not just elements. So it can be a compound. So essentially, we're looking at water. It's a homogeneous. It's homogeneously just H2O molecules. All right. So we're looking at the atomic view. We can see that if we were to isolate a certain volume, we can only find one type of substance. So for pure iron, it would just be a metallic structure of iron atoms, iron ions, and it will basically be not adulterated with anything. Okay, and for water, it would just be H2O molecules. So as a result, a pure substance cannot be separated by physical means, simply because what is there to separate? All right, apart from the primary material itself. So yeah, we can see that we can therefore not separate it, because there's nothing to separate. And if we were to look at the melting and boiling point spread for the pure substance, if we were to do a constant heating graph, we can see that the equilibrium state, whereby solid and liquid of that substance can exist, or liquid and gas, basically the melting and boiling point, we can see that when we were to extend this towards the y-axis, we can find that there's only one temperature in which this equilibrium states can exist, and whereby the melting point and boiling points are at certain temperatures. All right, so there's basically no range. Now, when we're looking at an impure substance, we can see that there are other substances mixed in it. It can be a mixture or an alloy. So we can look at salt water. We can see that there's a mixture or a dissolved solution of water and salt. Steel would be an adulterated mixture or an alloy of carbon and iron, and maybe other elements in there. And air, which is a mixture of gas. If we look at this in atomic scale, we can find that there are many types of molecules within our control volume. There can be, such as for air, it would be a mixture of many different gases like nitrogen or water molecules, as you can see. And for something like on the right would be stainless steel, where compared to our first pure structure of iron, we can see that there's an adulteration of atoms like chromium and carbon, and they're there for good reason. They're there to improve the appearance of our iron structure and to improve its corrosion resistance. And this therefore makes stainless steel a much more viable option than pure iron in very many cases. So as a result of the adulteration and a mixture of substances, the impure substance can be separated by physical means. We can separate the pure substances inside our impure substances. All right. So we do this through processes like filtration, evaporation, distillation, and chromatography, which I will talk about separately, each separately in detail in a different video. So as a result of this, we can see that will be a range in which the melting point can exist and the range in which the boiling point can exist. So the equilibrium state between solids and liquids, or the melting points, will be existing in a different range, and there will be a range for the boiling points too. So there will be no distinct boiling and melting point, all right? So as a result, we can use melting and boiling point testing as a test for purity. If our substance is simply pure, then we will observe that melting will take place at a certain temperature and boiling will take place at a certain temperature. And it would be opposite the melting point and boiling point would be existing in a range for our impure substance. And another important thing to realize is that for impure substances, melting will take place at a lower temperature than pure substance, and boiling will take place at a higher temperature. This is a very interesting discussion, which I will talk about in another video in detail. So to quickly summarize our video, we will know that a pure substance is simply a substance that has nothing else mixed in it. A pure substance cannot be separated by physical means, whereas an impure substance can be separated by physical means, whereby we're trying to separate the pure substances inside our impure substance. And the melting point and boiling point testing will be a test for purity, because for an impure substance, melting point and boiling points have ranges, and for an impure substance, recognize that the melting point is higher and the boiling point is lower.
Separation techniques. Filtration. This method is used to separate insoluble solid from liquid using a filter paper. The liquid mixture is poured onto a funnel that has a filter paper. The filter paper allows the liquid particles to pass and fall into the flask, forming what is called the filtrate, while the insoluble solid is left onto the filter paper, called the residue. Evaporation, to dryness. This method is used to separate soluble solid from liquid, by heating the mixture in an evaporating dish, until all the liquid evaporates and the soluble solid is left. Crystallization. This method is similar to filtration, used to separate soluble solid from liquid as crystals. The method is same, however, as the liquid evaporates, the solution turns into a saturated solution. This means, no more of the solid can be dissolved in the solution at that temperature. Decanting. Decanting is used to separate a dense and soluble solid from liquid, by pouring the liquid away. Sublimation. Sublimation is used to separate a mixture of solids when one of them sublimes, meaning it turns from solid to gas without becoming a liquid.
Welcome back to freesciencelessons.co.uk. By the end of this 4-part video, you should be able to describe physical separation techniques. Now these include filtration, crystallization, distillation, and chromatography. In this video, we're going to focus on filtration and crystallization. Now the first thing I need to point out is that physical separation techniques such as these are used to separate mixtures only. They can't be used to separate the elements in a compound. In later videos, we're going to look at how we separate the elements and compounds, for example by chemical reactions such as reduction or by electrolysis. But in these videos, we're focusing on physical separation techniques and how they're used to separate mixtures. We're going to start by looking at one of the simplest separation techniques, which is filtration. Filtration is used to separate an insoluble solid from a liquid. Now remember that the word insoluble means that a solid will not dissolve in a liquid. So I've got here two chemicals. On the left we've got silver chloride and on the right we've got water. These small letters are called state symbols and they tell us the state of a chemical. For example, whether it's a solid, a liquid, a gas, or whether it's dissolved in water. This little s tells us that silver chloride is a solid. The little L here tells us that water is a liquid. Now, silver chloride is actually insoluble in water, so it will not dissolve, and you would be given that information in the exam. So I have a solid material suspended in a liquid, and I'm showing you that here. Now, obviously, this diagram is not to scale, as you'd not normally be able to see individual particles of silver chloride, but you should get the idea. So because the silver chloride is insoluble in water, we can use filtration to separate these two substances. To do this, we use a filter funnel and a filter paper like this. We start by pouring our mixture into the filter paper. The liquid, in this case the water, simply passes through the tiny pores in the filter paper. However, the solid material, in this case the silver chloride, can't pass through the filter paper, so it's trapped. So in the end, we've got our liquid separated from our solid. Filtration is a really useful separation technique, and it's used a lot in chemistry. Another important separation technique is called crystallization, so let's take a look at that now. Crystallization is used to separate a soluble salt from a liquid, so you can see that it's different from filtration. In this example, we've got sodium chloride and water. Now, the little AQ here means that the sodium chloride is dissolved in water. Scientists call this an aqueous solution. We want to separate the sodium chloride from the water. So here's our sodium chloride solution. If we leave this solution for a few days, then the water will evaporate. This will leave behind crystals of solid sodium chloride like this. Now, can you see that I've changed the state symbol for the sodium chloride from AQ to S, because now the sodium chloride is not dissolved in water. It's now a solid. If we wanted to make crystallization happen faster, then we can gently heat our solution to evaporate the water. However, we have to be careful that heating does not affect the chemical that we're trying to crystallize. For example, certain chemicals will break down if we heat them, so sometimes it's better to just leave the water to evaporate on its own.
Simple distillation. This method is used to separate a mixture of two liquids. As every pure substance has a distinct fixed boiling point, in distillation the mixture is heated to the boiling point of one of the liquids. The boiled-off vapor is then passed through a condenser that turns it back into a liquid which is poured into a flask.
And welcome back to freesciencelessons.co.uk. By the end of this 4-part video, you should be able to describe physical separation techniques. Now, these include filtration, crystallization, distillation, and chromatography. In the last video, we looked at filtration and we looked at crystallization. In this video, we're going to look at distillation, so let's get started. When we looked at crystallization, we saw that we can evaporate a liquid, such as water, from a solid, leaving us with crystals just like this. The problem is, what do we do if we want to keep the liquid? Well, in this case, we use distillation. So distillation can be used to separate a liquid from a solid if we want to keep the liquid. Now, I should point out that we call this simple distillation. There is another technique called fractional distillation, and this allows us to separate two different liquids. We're going to look at fractional distillation in the next video. So how does simple distillation work? Well, there are two stages to this process. First, we evaporate the liquid by heating. We then condense the vapor back to a liquid by cooling. Let's look at the apparatus that we use to do this. We place our solution with the liquid and the dissolved solid in this flask here. This flask is now connected to a continuous glass tube, which I'm showing you with this yellow arrow here. The glass tube is surrounded by a jacket, which we call the condenser. Cold water from the tap continuously runs through the condenser, and by doing this, it keeps the internal glass tube cold. After running through the condenser, the water simply goes down the sink. We've also got a thermometer as part of the apparatus here. So let's see how this works. We start by heating our solution, for example by using a Bunsen burner. As we heat the liquid, it starts to evaporate, turning into a vapour. This vapour now rises up the glass tube, like this. The thermometer shows us that the temperature is rising, but actually with simple distillation we usually just boil the liquid. The vapour now passes into the condenser. Remember that the condenser is kept cold, because we're circulating cold water around it. This means that the vapour now condenses, turning back into a liquid as it passes through the condenser, like this. We can collect the liquid in our beaker, so at the end we're left with crystals of our solid in the flask here, and our liquid is in the beaker here. So that's simple distillation. Simple distillation can be used to produce drinking water from seawater. However, a great deal of energy is required for simple distillation, so generally it's not used to make drinking water. Other techniques are used instead. Okay, so hopefully now you can describe how simple distillation can be used to separate a liquid from a solid if we want to keep the liquid.